Right. So let me summarize what we discussed in the last lecture, that the universe actually in our neighborhood, we're right in the center of this picture, we are part of this Virgo cluster, and then there are these huge superclusters around us. We are moving towards Shapley in that direction according to the cosmic microwave background dipole anisotropy, and there are various other superclusters that we have mapped out. So this is the typical depth of the redshift surveys that have been done to date, and the point is that we have to now make some sense of it. So I'm going to now proceed in the standard way, but I hope I have sowed the seeds of doubt in your mind as to whether it is really justified to approximate it as homogeneous, and in particular, are all observers the same? I mean, it did not make a difference as to what I deduce about the universe according to whether I'm located in a supercluster or in a void. Does it not matter what direction I look? We should really start asking questions about what direction surveys have probed. Sometimes maybe whether willingly, deliberately or not, they have looked for directions which are, I don't know, free of dust or free of intervening matter or something. So then you would really tend to deliberately look along directions which are mainly voids, and their expansion law might be different from that of a direction which is mainly clusters, because of course gravity responds to the local matter density. So you're not going to have the same speed of expansion everywhere in this space. Yeah? No, we know our place in the universe. We are right there. We are right at the center of this picture. Okay, we know where we are. This is what the universe actually looks around us. We do know our place in the universe. The question is that place in the universe special in any way? I'm saying that we have this Copernican prejudice that we should not think of ourselves as special in any way. But in fact, we have to accept that we are in some particular place, and that will color our impression of the universe we see around us. Okay? In the sense that, like, for example, the fact that you are moving through the CMB, right? There's nothing special about that frame. If I do an experiment in a closed laboratory, it will give exactly the same result in that frame as in any other frame in special relativity, right? The question is whether that has some cosmological significance. That's a separate question. Okay? Cosmology is not about local laws. I'm asking whether there could be a bigger framework in which that has some significance. We don't have such a framework. We're just looking at the data. Right. So having said all that, now I'm going to take you through the standard cosmological construction just to make it clear why it is so difficult to study any alternative cosmology. It is complicated enough as it is, right? So now this is something that some of you have probably already done courses in GR and cosmology. What, about half? Who has done? Raise your hands, please, those who have done a course. Okay, about a third, so not too bad, thank you. Then I shall go through it relatively quickly, but for the benefit of those who haven't, I'll just point out the key aspects. So the first thing you have to do in order to set up some mathematical model is to have a metric. You have to have some ways of measuring intervals, right? And you know that the standard interval in special relativity, that is the Minkowski metric, is this object here, and this is a 4x4 matrix. It's symmetric, so there are 10 independent components, and in fact we have, in the case of flat space-time for the Minkowski metric, we have just this simple diagonal form, and the interval for space and time is just this. You can have a similar one for energy and momentum. Now this is invariant under Lorentz transformations. So this is the same as the local inertial coordinates of Newtonian mechanics. And this was the first problem that was faced when people wanted to construct a world model, because it had been decreed by Ernst Mach that the inertia, okay, is something that Mach believed was something related to the large scale distribution of matter. So today we have a different view of what inertia is or what mass is. We believe, for example, that mass is due to, I don't know, my interaction with some all-pervasive Higgs field or something. Okay, it's a completely different approach to the question of inertia. But the historical notion of inertia actually had to do with something very, very interesting called the rotating bucket experiment of Newton, which I won't go into here. But there are interesting questions with regard to mechanics which are still debated and discussed today. And they all relate to this question of what determines inertia. The problem that Einstein faced was that Mach had decreed that inertia is related to the large scale distribution of matter, but you can see here that if you had no matter at all, then the solution would be the Minkowski metric, and that therefore is defining an inertial frame in the absence of matter, which is contrary to Mach's principle, right? Now, I don't know if this might all seem like hocus pocus to you, but at that time it was very important, okay? For Einstein it was very important. And maybe you're not so persuaded that it's a real problem. But because Einstein wanted to obey Mach's principle, he saw two ways out of that conundrum, that in the absence of matter you're reduced to the Minkowski metric of special relativity, and that then apparently allows you to have a notion of inertia independent of the distribution of matter. So one possibility was make this Gij take some pathological form when away from all matter, right? In that case, you don't violate Mach's principle, but De Sitter, who was more sensible, wrote to him to say that's complete nonsense, because when you look at a distant star, the light is coming to us through empty space. If something funny was happening in empty space, then we would not see stars as they are. So don't mess with the metric. Okay, that was the advice that De Sitter, he wrote a letter to Einstein pointing this out. So Einstein therefore went to the second possibility, which is that you assume that the matter distribution is homogeneous in the average, and that space curves in on itself, right? So this is the famous analogy of the balloon that he chose in order to have a volume that is finite but has no boundaries, right? Now this is of course the model that has survived. So basically everything that we are doing now is 100 years old, okay? The model of cosmology that we are using now to interpret data is 100 years old. I don't know of any other field in physics where we are still using a 100-year-old model. Now the key thing was that it had homogeneity, and so as I explained to you, this was actually observed much later in 26, Hubble's law. This is actually Hubble's law. Not what you think is Hubble's law, that velocity proportional to distance. That is not Hubble's law. That is an automatic property of any homogeneous space-time. And Hubble never said that. Hubble never interpreted redshifts as due to an expanding universe. That is another myth. I'll tell you why. I'll tell you where you went wrong. So if you incorporate this cosmological principle that in fact you are at a typical point and that therefore homogeneity extends to the whole of the space-time, not just around us, then you can construct a metric which allows for having definition of world lines in the usual way. You have synchronous observers, these mythical beings all carrying clocks and rulers who can synchronize with each other, and thereby you have a description, a construction of a world model. And as I said, this is the century-old model we are still using. Now, how do you set up this metric? Well, basically you picture the spatial part as a surface of a sphere, a S3 in 4 dimensions. And so this is a construction which is tried to suggest, I can't draw a 4-dimensional sphere, so this is a construction that suggests that you can think of two polar angles, two angles, one polar angle and one azimuthal angle, and you can then see that there is a little radius, which is the radius which is extending out from this axis, and then there is the bigger radius, which is the radius which is going radially out like that. That is capital R, and this is little r, okay? So if I write down the set of points that defines this surface, that's just x square, y square, z square, and w square. W is the notional 4th dimension in which my 3-dimensional sphere is embedded, right? Just as the Earth is a 2-dimensional surface, it's embedded in 3-dimensional space. This is 1 dimension up. But I also have another constraint, which is that little r squared. This little r squared is just the sum of the three spatial dimensions. So then if I write down the line element, I can just replace this dw square by r squared dr squared by capital R square minus little r square. And then if I convert to polar coordinates, then I can just write it in this way that is already beginning to look familiar to you, right? And or I can write it in terms of the sine chi, where chi is the polar angle of this hypersphere, right? And already when you construct a curved space like this, you already can start seeing lots of interesting effects. So for example, if I'm sitting here and I'm observing somebody taking away a standard rod away from me, but constrained to the surface of this sphere, this S3, then I will already start seeing interesting effects, such as that the angular size, which is by definition from here given as the intrinsic length d divided by r sine chi, this will reach a minimum when this person that I'm looking at is 90 degrees away from me. And when that person goes to the antipodal point of this sphere, then it will fill the whole sky. Okay? So this is why. So this is the explanation for why you might have sometimes have thought about this, that when you go back, you know when you look out in distance, you're looking back in time, and we are supposed to have originated from a Big Bang, which is supposed to be not a point in space and time, but everywhere. How can there be something everywhere which is still a tiny point and covers the whole sky? It's very simple. You are sitting on the north pole of a sphere, and the Big Bang is the south pole, and all the light from it is constrained to come to you along the surface of this hypersphere. That's all there is to it. So if you think in terms of non-Euclidean geometry, it is immediately obvious what we are looking at when you look at the sky, and also that makes it clear that there is no preferred point on this sphere, all points are the same. So therefore, we look like we are the center of the expansion, but anybody else on that sphere also thinks they are the center of the expansion. Okay? And that is why the Big Bang is not localized anywhere, it is everywhere. Right? It is the antipodal point of the hypersphere. So this simple exercise already teaches us a lot of very interesting things. Now, if you are interested in this, by the way, there is a very amusing little book by Gamow called Mr. Tompkins in Wonderland, where he discusses what would happen if these curvature effects were actually important on the scale that we actually live in. We don't. We live on a flat Earth, right? Yeah?
Can you give me another example?
Of what?
You said that we live in a North Pole,
the
Big Bang is South Pole, and we see the Big Bang all over the sky.
Yeah. Well, I can move to the equator, and then the antipodal point will be my Big Bang. It's the same thing.
But now we think about we talk about the sphere, right?
Yes.
But if it's not a sphere, can you give me another example?
You mean you want it to be a potato?
What about a cylinder or something else?
No, okay, cylinder will be different. A cylinder has an axis of symmetry. The sphere doesn't have one. You could have a cosmological model which is closer to a cylinder, for example, a rotating universe, and Gödel gave such a model, right? Which would have a axis of symmetry, it would have angular momentum. There would actually be the interest in that model is because it has closed time-like curves. You can do time travel in that universe, right? But we are restricting ourselves to a simpler one, right? Yeah?
Considering we are on the surface of a sphere, a floating sphere, would it be possible, hypothetically, if you have a very great telescope which has infinity angular resolution, that we look out to the space and we see ourselves?
Yes, you can see. You can see your back. Sure. In fact, at some time when we were seeing the periodicity in the distribution of quasars, people thought we were doing exactly that. In principle, because it's a bounded space, right? So yes, you can actually see multiple images of the same thing, but we'll come to a more interesting aspect of that shortly. I have one slide about topology, which actually makes it even more interesting. Okay, so this is the straightforward stuff. You know that you can have the space-like sections can be flat or positively curved or negatively curved like a saddle, and that according to whether lines meet or don't meet or diverge, and the angles add up to 180 greater than or less than. Incidentally, if you can try to do this on the Earth, and Friedrich Gauss, the famous mathematician, actually tried to measure this to determine the curvature of the Earth by putting lanterns on hillsides and trying to measure the angles between them. So of course the Earth is actually pretty flat. It is very hard to measure the curvature doing that, but you can see the curvature of the Earth at sea. So for our universe is a bit bigger. Yes. Now, I'm just throwing out some interesting ideas that people have discussed. So, for example, we now believe that our universe is actually something like a Euclidean universe. The space-like sections have got zero curvature, so that we don't in fact have, it basically extends to infinity. But actually you don't know that because you only observe up to the Hubble radius, and in principle it could be that our universe has got a much more complicated topology than that. And this particular topology came into fashion some years ago when it looked like there were patterns on the sky in the cosmic microwave background that appeared to have a reflection. So it was like being in an infinite hall of mirrors and seeing the same thing again and again. And now that evidence basically has gone away, in the sense it turned out that statistically you cannot claim that apparent repetition of the pattern is significant. But in principle, so all you can now say is that the scale of the topology is as big as the Hubble radius, so of order 10 gigaparsecs. But if you want to know more, here is some references to this guy Lumine, who has written a lot about it. So going back to the way that the standard model was constructed, so the next steps were taken, as you know, by Friedman and most importantly by Lemaitre, who pointed out that that line element you could now make dynamic just in that one scale factor, leaving, because you want to maintain isotropy and homogeneity, so you don't touch this angular part at all. You just look at the radial part and you make that time dependent. So you can have a self-similar expansion, for example, of a triangle. All the angles remain the same as the expansion happens, right? So you're not actually expanding, you're stretching the scale of space-time. Similarly, you can have an open universe, you can have a closed universe, and this is the Robertson-Walker line element, which Robertson-Walker wrote a classic paper about. This is the maximally symmetric space-time you can have in this setup, okay? And that, you have to be careful about the dimensions. The way I have written it here, this guy is dimensionless. And this part we normally don't ever talk about, because this corresponds to things to do with departure from isotropy, which we rarely consider. We really only ever consider the radial part. And I'll give you an example of a different cosmology, the Talman Bondi model, where actually there is a radial variation of the metric. So essentially the universe is, this is taken from a nice article in Scientific American, which used Escher-like paintings to try to illuminate what it is like living in a universe with negative, zero or positive curvature. So according to the microwave background data, we are living in a universe that looks like this. And obviously the real universe is not filled with scaffolding, but if it were, then it would look like that. Okay, so that's very interesting. Yeah. I have not yet come to that, but yeah, go on.
I mean, the asymptotic behavior of our universe should be de Sitter.
That would be de Sitter then, yeah.
So where does that fact?
De Sitter would come when the behavior of that scale factor A, so it has got nothing to do with this metric part. But I'll give you the construction of the de Sitter metric later, which is where Hubble went wrong. I'll show you. So homogeneous and isotropic world models are basically that geometry. These are the possibilities, and this is how you evolve with time. So this guy will expand and then collapse again, and these two will keep expanding forever. This will asymptotically go to infinity. Now, the redshift, this is of course the most important part of this exercise, because what you actually observe are photons and you have to interpret what you measure in terms of the cosmology, right? Everything is interpretation. We are not directly measuring the scale factor. We are interpreting the redshift as a change in the scale factor. So why is the redshift happening? Because if you look at a null geodesic, okay, so the interval is 0, then you can simply work out if I have a wave with some separation between the crests of a certain wavelength, then I can ask what happens to that when I observe it when the scale factor of the universe has changed, right? So when I do that, I find that the wavelength will be different, and the difference in the wavelength is just the scale ratio of the scale factor at the time of emission to the time of observation, just from looking at the null line element, right? So effectively the wavelength of the light is, if you like, being stretched out by the expansion, and this is the famous redshift, okay? Obviously if it goes in reverse, you'll get a blue shift. Now this is the time dilation. So the antipodal point of the hypersphere that I was talking about, which is the Big Bang for any observer, that would correspond then to infinite redshift, right? Because the light from there is going to cover your whole sky, and that at that singular point the redshift will be infinite. We can't actually look back that far, because long before that the universe becomes opaque, it becomes too hot, photons can't propagate through it, then at some point neutrinos can't propagate through it. It is still possible to look back to the Big Bang using gravitational waves, and that is something that people have started thinking about now. Now there are lots of nonsensical discussions about the expanding universe. Most of it have to do with the word expanding, okay? Because if you say expanding, then the next question is expanding into what? There is nothing except the metric, okay? We've constructed the metric, that is our description of this mathematical model. No, do not ask questions which go outside the metric, because that doesn't exist. In this universe only the metric exists, right? So in practice what we are saying is that things are not expanding, everything is not expanding, because then you would not know. So effectively the large scale smooth space-time, in other words that underlying background that we talked about earlier, which is stretching, right? And this is actually completely illusory, because I can just transform to a frame where I just take it out completely, I go into the co-moving frame, there is no expansion, right? The galaxies are at rest with respect to each other. So there is no such thing as the expanding universe. And in fact, Hubble never used the words the expanding universe. I'll show you his actual quote. So this universe needs to have something to fill it, and in accordance with our overall philosophy of keeping life simple, exact homogeneity and isotropy, we fill it with an ideal fluid which has no vorticity, no off-diagonal elements, no viscosity, no funny stuff, none of the things that Andre told us about. This is a very simple fluid. It's an ideal fluid with a diagonal energy momentum tensor. It obeys Poisson's equation. The only thing we have borrowed from general relativity here is that to the rho, normally it would be 4 pi gn rho, I've added 3p. Why is that? Because P is energy, P is kinetic energy, that's the pressure of gas, right? And according to Einstein, all energy gravitates, pressure also gravitates, so you add it to the energy density. But everything else goes through, in particular Birkhoff's theorem, the iron sphere theorem. So if the energy momentum tensor is 0 in some region within some spherically symmetric distribution of matter, then the solution in that hole is Minkowski, okay? The rest of the universe does not matter, it just cancels out. That is a very powerful theorem. So in this universe, these individual galaxies are supposed to be moving with sort of, world lines that do not intersect, right? This is actually a bit different from the real world of galaxies we saw in the last lecture, which do meet up, cannibalize each other, all kinds of things. But to a broad approximation, this holds when averaged over sufficiently large scales. That is the belief. So now you have dynamics, you have to bring in Einstein's equations, which would relate that metric that you constructed and the curvature tensor, etc., that you constructed from the metric to the energy momentum tensor, for which you have assumed an ideal fluid coupled to Newton's constant, right? And these are the quantities that enter into it. Deceptively simple, and actually horribly complicated, so much so that the only solutions that we have been able to get in cosmology for actual use, particularly by astronomers, are the simplest possible ones with the maximally symmetric spacetime metric. Okay? The real reason why we are doing cosmology with a 100-year-old model is because just departing even a little bit away from the model makes it horribly complicated. So I'll show you later what a Lemaitre-Talman-Bondi model looks like. That's just one little departure, and it's already pretty complicated. So for the Robertson-Walker metric, the 0011 components will give you the Hubble equation and one for the deceleration, where in fact this gravitating energy density enters as before with rho plus 3p. Right? This is also contributing to the energy density, and you can see that the equation of state will then determine whether this net sign is positive or negative. So because we have the Newton ion sphere theorem, Birkhoff's theorem, we can do Newtonian cosmology. In other words, forget general relativity. We just consider a little sphere embedded in some homogeneous background, and we ask for a test particle on the surface of the sphere. It will suffer an acceleration under gravity, which is just given by Newton's law. The mass in there is this. This is the GR. I'm sneaking in GR by the back door because I put in a 3p there. That has to be there. So the amount of gravitating mass inside that sphere is 4 pi r cube times 4 pi L cube times this guy here. And we also have the second law of thermodynamics. So putting the two together, we can then work out whether this thing expands or contracts. The work done by the pressure will have to be taken into account, and that gives us this conservation equation, which you are familiar with. So I'm just very quickly retracing for you, I'm conscious of the time, all the things that you know to show where they actually come from. So the acceleration equation can now be simply integrated to give you the equation for the velocity, and there is an integration constant. And here in this context, the cosmological constant actually appears, not usually, but only in this context as the integration constant. So Einstein in fact wanted a static universe because he, as I told you, didn't know any data, and at that time we had barely got to realize that we live inside a galaxy, far less that galaxies have redshifts. So he considered the possibility that you have rho plus 3p equal to 0, and that would then uniquely define the radius of the universe, which is this one here. In fact, something pretty close to this is written down on a blackboard in the Museum of History, Museum of the History of Science in Oxford, where he gave the Rhodes lectures in 1930, right? But this is actually not a good idea, because this solution is unstable. If you perturb the metric, you'll find that the metric perturbations grow exponentially, right? So in fact, you cannot have a static universe. It is unstable towards metric perturbations. So, and in any case, whether or not you have a constant in the equation is not a choice to be made by Einstein or anybody else. It is a consequence of general coordinate invariance. There was a question earlier about the connection between conserved quantities and symmetry principles. This cosmological constant that we are about to introduce is a necessary consequence of covariance. Okay? So that means we should be able to allow any term which is multiplying the metric to be added to the left-hand side of the equation that preserves the symmetry. Okay? And this term is not determined by anything that we know, right? In fact, you can interpret it as a fluid with negative pressure, and that was soon done by Lemaitre, who in fact moved it to the right-hand side, but that is a matter of choice. The point is that there are two separate cosmological constants. One is coming simply from the freedom granted by general coordinate invariance, and actually you'll see that once we go to treating Tij not just as a ideal gas or a dust as it was called, but as a quantum field, then in fact it has a super-normalizable term in the Lagrangian which also acts as a cosmological constant. So there are two cosmological constants, not one, and that is the real cosmological constant problem, that these two things do not know anything about each other, and yet they apparently do, or they must do in some way. So now we are getting to the modern form of this FLRW dynamics. So I have now decided to split things into a background, this B is for background, so that is ordinary matter and radiation, to distinguish it from this lambda term. So I now write down the equation for the acceleration in terms of the thing that we had before, and there is also this curvature term. And then you have the conservation of energy momentum, which follows from the same second law of thermodynamics that we had earlier. And so finally we have the Hubble equation, the Friedman equation, which says that A dot by A, which is defined as the Hubble parameter, just goes by 8 pi g rho by 3, and Tracy and others use this in their calculations for dark matter freeze out and so on. And now you have this choice for this term as to whether the space-like sections are flat, open and closed. And so you have two solutions for this equation which were initially studied. One is the possibility that there is no pressure at all, you just have dust, non-relativistic matter, and you have no cosmological constant and you have no curvature, in which case A goes as T to the 2/3, you have a precise H for the universe in terms of the Hubble parameter related to the density, right? And the other universe that De Sitter presented had no matter at all, but just a cosmological constant, and that one expands exponentially fast, right? So this was the counterexample at the time to Mach's principle, which had decreed that you could not have a notion of inertia without matter, and this was the first counterexample that was given to that. Now this stuff you all know, but something you may not know is this. De Sitter actually presented a third solution which looked like that, okay? And when he first presented it, people sort of didn't quite realize what this metric was. It looks like a static metric, and it has this peculiar property that if you look at a clock which is at rest, okay, at some point, so let's say this interval is 0. Now look at the time-like interval, right? So that is just dt squared times 1 minus r squared, little r squared by capital R squared. Now this depends on the radial distance little r. Okay, so as r increases, this interval decreases, right? And that is exactly what would give you redshift of light from a distant source. So this was called the De Sitter effect, that in this metric, the further away the source is from the observer, the smaller is the time-like interval, i.e. correspondingly the greater is the redshift of a standard wavelength of light emitted from that object. So in this case, the wavelength of the redshift we can calculate simply from that metric. So in the approximation that I can expand this in a Taylor series, so that is 1 plus r squared by little r squared by capital R squared, I get that the redshift, which is defined as lambda minus lambda naught by lambda naught, is simply half of little r squared by capital R squared, okay, where this distance is small compared to the internal curvature scale. Now this therefore would lead you to expect a quadratic relationship between the redshift and the distance, and this was called the De Sitter effect. And lots of famous astronomers and Hubble himself went looking for the De Sitter effect, and they found it. They fitted the data to the De Sitter effect, okay. In fact, De Sitter later realized that this relationship has to be linear, because in any homogeneous space-time, you can only have a linear relationship between the two. Okay? You cannot have a quadratic relationship. The point is that this is actually De Sitter space. There are no inertial observers in that space. All observers are accelerating in that space. But this was not obvious initially, and Hubble in fact fitted the redshift distance data to a quadratic relationship. Look up his paper in the Proceedings of the National Academy of Sciences, which is widely cited but perhaps not as widely read, and you will find that he has said in the end that I think there is evidence here for the De Sitter effect. And when he realized he had blundered, because De Sitter wrote to him to explain, oh sorry, I didn't realize that my metric was actually a weird sort of object. And Hubble said, the interpretation we feel should be left to you and the very few others who are competent to discuss the matter with authority, right? So these days when somebody makes one incorrect measurement of a supernova, which then makes the equation of state of dark energy in -2 or something, phantom energy or something, I somehow think that maybe they should have read this thing by Hubble, right? So here you have it, the evidence. Hubble never talked about the expanding universe. He was actually very, very pragmatic. He measured redshifts, he knew distances, and he waited for the theorists to tell him what it meant. That is how it should be. Theorist. Friedman had found the expanding solutions earlier, long before there was any data. Friedman did. Friedman was actually a meteorologist. He was everything, but he didn't have astronomical data. That came much later with the work of Westo-Slipher. Yes, but because Einstein, the great man, did not take any notice of it and didn't like where it was leading, and Einstein never wanted to look at the data at that time. So opportunity was missed. I agree with you. It could have been that it could have been seen as amazing. The history of cosmology is full of amazing predictions which were completely ignored, and the cosmic microwave background was predicted, and it was even found, okay, and not realized for the finding, okay. That is to say, nobody recognized that somebody was finding that all molecules appeared to be excited as if bathed by a 3-degree bath of radiation. This is Makela. People just ignored it, right? Because somehow the really weird thing is that at Bell Labs there was a man called Ohm, no relation I presume, who actually was measuring the noise from the same horn antenna, and he recorded that there was an unknown source of noise, okay, of order 2 ± 1 degree K. Okay, and Zeldovich had he published in a journal called IEEE, which is for engineers, IEEE Proceedings. So apparently Zeldovich read this paper in IEEE and decided that, oh, this means we have to think about a cold universe, because these observers have said that there is no radiation from the Big Bang, right? Because Zeldovich didn't appreciate that 2 ± 1 did have a 3-degree in it. Right? So it's an amazing story of the missed opportunities like that. Anyway, after all that work, we finally have the set of the simple Friedman models, right? So I've already mentioned the Einstein de Sitter one that goes asymptotically to infinity. There is, of course, the bouncing universe model. Then you could have a model in which you have the Lemaitre model, which is got a cosmological constant that dominates for a little while. So the expansion sort of goes almost constant and then goes de Sitter. So what you actually see is that by construction, as long as you have a lambda term in the equation, because that will inevitably lead you to an exponential expansion, it will always come to dominate at late times by construction, because everything else is redshifted away, right? The matter and the radiation. So you would always expect in a theory model, I'm not talking about real things now, you would always expect this, and this is a feature of the theoretical constructs, right? So in fact, the discovery of cosmological constant was an accident waiting to happen, because the theoretical models are constructed so as to, predict it, if you like. But in fact, keep in mind that when you make these precision measurements of the cosmic microwave background, we are actually observing an exactly Einstein de Sitter universe, because the microwave background decoupled at a redshift of around 1068. At that time, the matter density was 10 to the 3 cube, 10 to the 9 times smaller than today, and omega was within 1 part in 10 to the 12 of 1. I mean, it was almost exactly 1, right? So it was Einstein de Sitter universe. Now, this peculiar thing about this Robertson-Walker metric is that, unlike, say, the Schwarzschild metric, you don't actually go to Minkowski at r of infinity, right? But you can try to make it look like a Minkowski metric. If you want to do that, then you have to go to something called conformal time. You have to divide the time interval by the scale factor. Now, this makes it look superficially like a Minkowski metric. In fact, it's conformal to it. But it's actually quite dangerous, because this object here, you can see it goes to 0 at t of 0. So you have to be very careful. You should have a special license for playing with conformal time. You can be very misled if you don't know what you're doing with it. Now, there are other possible metrics. So we have so far considered only the maximally symmetric Robertson-Walker metric, and I told you what the historical basis for that was. It was the assumption of exact homogeneity and isotropy. So then I showed you data in the first lecture which suggests that homogeneity assumption is really something that needs to be yet demonstrated. It is not proven. And so you might wonder if there are less symmetric metrics that you can work with. And sure there are, but they already start getting very complicated. So the point is that we are now going to use this as a toy model, because if I use any other metric, for example this Lemaitre-Talman-Bondi metric, this describes an universe that is inhomogeneous but isotropic around our position, and immediately people will jump up and start saying, oh, you are going against the Copernican principle, we are not at any special point. I mean, it's supposed to be a toy model. The universe around us from our particular vantage point may well be approximated by an LTB model for some purposes. Of course, the problem really is that in order to do full-scale cosmology, we should also be able to describe how it came to be like that, starting from some initial conditions, right? And that is what is really hard to do. In any cosmology other than the FRW cosmology, it's very hard to start from, say, the little fluctuations in the cosmic microwave background and work forward, just use the theory of gravitational instability to then show you the universe as it is today. But already you can see that the freedom that such a less symmetric metric would allow you is, for example, the possibility of having some functional radial dependence. So the radial dependence is no longer the simple one of the FRW metric. You can have some arbitrary function there, right? And then you could in principle have a match to data in the radial direction, in other words in the redshift direction, which has a completely different interpretation in the FRW model, right? So I'll show you an example of this data later, but you can actually fit the data on the supernova Hubble diagram simply because we are located in a large scale underdense region, because what you are really measuring is a difference between the apparent magnitudes that you expected in the standard model and the ones that you really observe on the sky. They're 30% different. It could be that 30% is due to the variation of this radial part of the metric, not due to a lambda, right? So obviously at this point other kind of considerations come up. So people think that there is something particularly simple about the FRW metric, and indeed it is the maximally symmetric one, but it also allows of this lambda term. Actually, so does LTB. They don't address the cosmological constant problem at all. So the point I'm making is that one does not need to be bound to the standard formulae if you are prepared to accept that we are not necessarily living in an exactly homogeneous isotropic universe. But observationally, if you want to be as model independent as possible, you might simply want to expand the scale factor in terms of the first derivative, that's the Hubble parameter, the second derivative, that's called the Q0 parameter, and it is defined in this peculiar way because it was expected to be, the deceleration was expected to be a positive quantity because this gravity is attractive, and so they defined it with the minus sign in order that it would come out as a positive number, but in fact the surprise has been that it actually appears to have an excursion onto the other sign. You can invert these relationships. These are all for sort of historical interest now, because today you would do all this numerically anyway, but basically all these expansions are pretty good to within 6% out to a redshift of 0.4, which is, most cosmological astronomical data are actually pretty much local. Only when you go beyond a redshift of 1, which you can do with the Hubble Space Telescope, because by the time the spectra have been redshifted into the infrared, you can only observe it from outside the Earth's atmosphere. You can't study that from the ground. So you have to go into space, and that's very expensive. There are far less objects observed. So for example, we have 828 supernovae observed from the ground, but only about 14 observed from the Hubble Space Telescope. So that gives you an idea of the relative ratio. And then of course you can work out the actual coordinate distance. So this is the kind of thing that you might want to know if somebody asks you how far away is that galaxy, whatever that means. Who cares? I mean you just care about the redshift. But the important quantity that comes out from this discussion is the measure of the distance. The luminosity distance is defined as so it is basically the same as you'd expect for flux conservation, but now in this particular metric that we have chosen to work in. Okay. So the apparent luminosity of a source which has got some absolute luminosity, so many ergs per second, is then given by this little l, defined in terms of this luminosity distance. And since the scale factor is determined by the Friedman-Alpha Forest equations, you have then a relationship between what you actually measure and the quantities that you want to extract from the data, namely this Q naught and H naught. And you, therefore, if you can measure the absolute magnitudes and the redshifts, then you can extract that by fitting to this relationship. Okay. The intrinsic luminosity is related to the absolute luminosity in terms of this this formulae through this little algebra, which I will not waste time on. You can go through this exercise yourself. But this is all in the textbooks. This might even be in Weinberg's classic textbook, which is still pretty good, I think, even though he used the opposite signature to what people use. But it's still a very good book. I'm talking about the old one. I'm not so fond of the new one. Anyway, this gives you the magnitude redshift relationship. This is what the observers actually use, because I told you they don't talk about the absolute luminosity. They take its logarithm and then they multiply it by minus 2.5, and that would then give you numerically a relationship between magnitude and redshift as so. And typically we don't know the absolute luminosity and we don't care. It's degenerate with the Hubble expansion rate. And we can then write Friedman's equation in terms of this time coordinate I've defined here, tau, which is h naught times t, as so, from which it is clear that as you go back further in time, as you go back up in redshift, you are getting closer and closer to omega of 1. And that is, of course, creates this famous fine-tuning problem of why is omega so close to 1, because it apparently would have to be almost exactly 1 to within 1 part in. So if you go back to the quark-hadron phase transition, it has to be within 1 part in, I can't remember, 10 to the 28 of 1. If you go back to the electroweak scale, it has to be within 1 part of 10 to the 32 of 1 or something. So it all seems like a very finely tuned universe, and maybe that is because that is just the way we constructed it. We'll see. But the point is that from these observations that you actually make of real objects, their magnitude and redshifts, you can infer the acceleration rate, and in this model you can relate the deceleration rate Q naught to the matter density and the fraction of the energy density in lambda. So they are defined as so. Omega lambda is lambda over 3 h naught square. So omega lambda being of order 1 means lambda is of order h naught square. Okay. Now I'm emphasizing this because this is the only scale that enters the Friedman equations. H naught, that's the only thing with dimensions. Okay. And therefore you cannot, if you are going to use this relationship to infer things, you will always have a sum rule that says 1 equals omega matter plus omega curvature plus omega lambda. I've left out the curvature here. And therefore, if you infer omega lambda from that sum rule, you're always going to get a value of order h naught square. Okay? And h naught in particle physics units is 10 to the minus 42 GeV. It's got nothing to do with fundamental physics. It's the rate at which the universe is expanding today. Right? Now, these equations are of course known for a long time, and in fact Sandage and others embarked on a quest to measure them. They thought this was the main thing in cosmology, but he gave up because of those evolution effects that I told you about earlier. He realized that galaxies change. They change, the numbers of galaxies change, the colors of galaxies change. You cannot actually use them as ideal objects such as is assumed in these relationships. So this was the problem. This is why Sandage never actually managed to measure the cosmological parameters. So for example, people try to measure galaxy counts. You can ask how many galaxies should I expect per co-moving volume, and you'll get a formula out of that machinery I've set up for you, which goes as this. And you might try to infer this. And when people did this exercise, there were 2 astronomers at Princeton who did this, they got omega of 1. Lambda of 0, okay? And then it turned out that, in fact, later that there was the galaxy counts, galaxy numbers are not actually conserved, they change. So that inference was, had a large systematic uncertainty, which was not under control. Similarly, if you have objects with got a standard ruler, if you know that the separation of a radio source, for example, between the radio lobes is some standard number, then you can use it, as Kellerman did, to try to infer again what the cosmological parameters are by looking at populations of double lobe radio sources at different redshifts. Again, you can go wrong if that is actually evolving with time rather than being a constant quantity. So there are pitfalls in making these measurements. So all these are restricted by evolutionary effects, and let me show you how easy it is to bias this. So if the luminosity is not a constant, as is assumed in all these things, but as let's got some linear dependence on the time, so the luminosity of some galaxy or supernova or whatever is L0 plus some number times T minus T0. It's growing linearly with time or decreasing linearly with time. Then when I go through the same exercise as above, I will find that there is this term is appearing here, right? And so therefore, if I try to infer Q0 without knowing that there is this luminosity evolution, I will find the wrong answer, because my answer has been biased by this unknown change in the intrinsic luminosity. Right? So the examples that I mentioned earlier, they're all documented in these review articles, and you can see there how easy it is to get the wrong answer for Q0 if you don't know about these evolutionary effects. Okay? There were at least 3 occasions on which a positive cosmological constant was claimed from the data, which later turned out to be wrong. Right? I gave you 2 examples here. However, recently there have been advances in finding objects which are close enough to standard candles that people feel now more courageous about using them to try to trace out this expansion history. And there are, as you know, this was in 1998, there are 2 teams, one led by Sol Perlmutter at Berkeley, and the other one, the High-Z supernova team, consisting mainly of people from Harvard, etc., Adam Rees and others, who concluded that when they looked at this magnitude versus redshift plot using that formula that we saw earlier, they saw a bunching effect around a trajectory that actually had a finite cosmological constant, rather than either a universe which was open with just omega matter of 0.3, or a Einstein de Sitter universe which should have omega of 1 and omega lambda of 0. Now, you can't actually see much from this because all those 3 models are laid underneath, and certainly by the naked eye, you cannot tell which line these data points fit best. Here, the difference is shown from the model that is expanding at a constant rate, which then does suggest that there is a clustering of the points more around this top line, which is the accelerating universe, this one. This is the decelerating universe. This is an universe expanding at a constant velocity, right? And this has been interpreted to mean that the expansion rate is accelerating. So this is a nice picture from a Scientific American article by Perlmutter, which shows that billions of years from today, and it shows some data points. Now, of course, the first thing you should ask is, how come Sol Perlmutter was around 10 billion years in the past making an observation? The answer is he wasn't. Okay? All these observations are made at one point in time, today. Okay? It is the redshift that is used as a proxy for the time. So there is already an intrinsic model dependence in anything that you do with this data, because you don't actually make measurements at different points in time. That era is coming with the very large telescope, the extremely large telescope, ELT, that is right now under construction in Chile. We will be able to see, over a period of 10 years, redshifts of galaxies actually changing with time, because the change is very, very small. It's only 1 part in 10 to the 9, but you can measure it with something called a laser comb. And so the era of real-time cosmology is soon going to be upon us, and that will be very exciting. But at the moment, we don't actually make observations in time. We make observations at a fixed point in time, and we interpret the redshift as a measure of the time. So that is why all these are theoretical models, and the data does fit the one where it first decelerated, then accelerated. But then I could draw another model which also fits that data, which didn't do that. But the bottom line is that this implies a cosmological constant which is of order, as I said, of order h naught square. In fact, it's about 2 times h naught square, because it's omega lambda is lambda over 3 h naught square, and the answer has to be close to 0.7, right? And if you want the gory details, there are some reviews I've cited here where you can look up how this happened. And this is the usual diagram that is shown to convince you that this is for real, which shows that the supernovae measure a quantity that's like omega lambda minus omega matter. That's why it's pointing up diagonally like this. Whereas the microwave background actually doesn't measure omega lambda at all. It measures the curvature of space-like sections, omega k. And therefore, if you measure omega k close to 0, then you lie on this diagonal line here, which is omega lambda plus omega matter equal to 1, and they intersect here. And then there are other much less certain measurements from baryon acoustic oscillations or the baryon fraction in clusters of galaxies and other such measurements, which all indicate that omega matter is around 0.3, and that would intersect it there. Okay. And so this, you stare at this plot for a while, and then you kind of get bored with it. And so then you say, all right, maybe it's not an exact cosmological constant, maybe it is some dynamical dark energy where the pressure is not exactly minus the energy density, but could be something close to it. So you define a equation of state parameter W, and then you start plotting W versus omega matter, and the data seem to be consistent with W of -1. But this is rather dangerous, because the way it was done like this, and in fact W was seen as a function of Z, because then you can integrate the equations for luminosity distance more conveniently for no other reason. But this plot has huge hidden pitfalls for a theorist. Okay, when you go down below -1, you are really going into terra incognita. Okay, you better have a license to violate unitarity and stuff like that if you're going to play with this. And that's what I meant earlier about one mismeasured supernova can make you think that you need an equation of state of -2 or something like that. Okay, just one mismeasured supernova at the high redshift end. But this is what we do these days, right? Now, let me finish this lecture by pointing out that actually the evidence for this ensemble is actually rather poor in particle physics terms, because the data that led to these conclusions was never actually made public. Okay, the one that from the supernova collaborations, they never put them on a public website so that you could download it and run fit it to the formulae and see if what they're doing was correct. Now, this was first done in 2016. By this collaboration here called the Joint Light Curve Analysis collaboration, and they show the sky map of 740 supernovae, whose basically the ones which are distributed all over the sky, they are the local supernovae. They are very close to us. They're within redshift of 0.2. Then there is this Sloan Digital Sky Survey that you saw earlier. That is that purple streak there. Okay, that's only in that part of the sky. And then there are these SNLS, the green points. So you see one green point here, one here, and the fourth one is hiding somewhere. There are just 4 directions in the sky that they looked at. This is why I showed you that picture at the beginning of the kind of local neighborhood we live in, to indicate that maybe things do matter. According to what direction you look at, you might draw different inferences. Anyway, this is the distribution of supernovae, and when you analyze this data correctly, I'll talk about it in the evening lecture, then you find that in fact the evidence for acceleration is actually not that impressive. And in fact that is easy to see, because in this plot the horizontal line is a universe expanding at constant velocity, i.e. without acceleration, and this purple line is the best fit lambda CDM line that we saw in the earlier slides. And this is the data, the actual data. So you can see it's very hard to tell the difference between those two. And indeed, the value of Q naught that you infer from that data is negative. It has a value of about minus 0.3, but it has a broad distribution, and about a fair fraction of it is actually positive. So the evidence that this Q naught is in fact negative, which corresponds to acceleration, is actually about 2.8 sigma. Which would not be particularly exciting if that was attributed to a new state found at the LHC, but that's the state of play here. Okay. Now, just to show you the games you can play, if you assume a different metric, so I told you about the Lyman-Talman metric, which has got a radial function multiplying that dr square, okay, rather than just a simple scale factor. And so you have two Hubble rates, right? One has to do with this variation of this guy here, and the other one is the overall scale. And so you have a modified version of the Friedman equation, and this was first propounded by Célérier. She's a mathematician in Paris, and she pointed out that you could choose a suitable density profile in which we are located in a, this is an example where you're located in an underdense region, but actually even that's not mandatory. You could be in an overdense region. But it is true that you have to have symmetry around you. You have to be at the center of this universe, not the universe, but this universe. And in that case, you can actually have a modified luminosity distance, and what you see here is the fit that you would get to the data from this Lyman-Talman model, which is indistinguishable from that due to lambda in the Friedman-Robertson-Walker model. So in other words, by expanding lowering the symmetry from maximally symmetric to something with inhomogeneity, but still isotropy, you can already match this data. So of course you have to look at other data, but this alone will not tell you what's going on. Now I've gone on long enough, so I'll just end on a positive note. The important thing is that most of the other data that I'll discuss in the evening lecture are indirect. The cosmic microwave background does not measure acceleration. The baryon acoustic oscillations measure a standard ruler, so that's a geometric test. It is not a dynamic test. So we really need to nail down whether this acceleration of the expansion rate is really up here as it is shown in the usual plots, or whether it really could be just a fluctuation and in fact the universe is not actually accelerating at all. How will you know for sure? Well, the way for know for sure is to make measurements in the time domain. So this is this extremely large telescope I was telling you about, which is right now under construction on this hilltop in Chile, not far from the Cerro Tolo mountain where the other telescopes are, where the VLT is. And what it will do is it will measure the redshift drift, which means the actual change with time of the redshift of a distant object. These will not be galaxies, it will actually be, for technical reasons, the Lyman-Alpha Forest, which I showed you in an earlier slide, which are clouds of hydrogen absorbing with absorption lines along the line of sight to a quasar. And the idea is that normally when you look at the spectrum of such when you take a spectrum towards a quasar, this is the Lyman-Alpha line. This is the line of hydrogen absorption, and shortward of that you should see absorption due to the intergalactic medium. In fact, there is no intergalactic medium, but you do see sharp lines corresponding to structures which are localized at least in velocity space. We don't actually know what sort of objects these are, whether they are extended, fractal. They are actually fractal in some cases, but they are not like clumps, they are not balls of hydrogen, because we can only measure in velocity space, but we do see these sharp lines. And if you monitor several hundred of these over a period of 10 years with this object called a laser comb, which can measure a wavelength shift of 1 part in 10 to the 8, the claim is that you will be able to measure redshift drifts, which are of the order of centimeters per second, for objects which are at a redshift of order 1, and the error bars that they predict on the basis of a preliminary study are indicated by these colored things here. So this is the accelerating universe, this is the decelerating universe. There clearly is possible to distinguish between the two in a definitive way by making this measurement. The only catch is that this will see first light in 2030, and then it will take about 15 years to do this. So we have to be alive in 2050 to know the answer to whether the universe expansion rate is actually accelerating. So thank you. I'll stop here.
So I'll ask a question.
Please.
I'm sorry that I missed a lot of
Not at all, no.
and I think maybe I missed the crucial point.
Huh.
It's very well established that the matter, dark matter plus baryonic matter, is an omega of about 0.3.
Correct.
It's also very clear from the cosmic microwave background that the universe is very flat.
Hmm.
I mean, within percent of flat. So what kind of cosmological model is consistent with that other than a cosmological constant?
Right. So let me just write that down here. So what he's saying is that in the Friedman-Robertson-Walker model he studied, the Friedman equation can effectively be written as a sum rule, right? And this is something like 0.3, and this is coming to be something corresponding to 0.
Yes.
And therefore,
And both of those two numbers are known quite accurately.
right, these are known quite accurately. Of course, they are known in different regions. This is known, omega of 0.3 is something that you inferred, well, in the past you inferred locally, now you can also infer it from observations of the CMB and the heights of the peaks with some model dependence.
Those numbers are totally consistent with each other.
Yes, yes. But they are completely independent measurements. These are nothing to do with each other. Now, omega lambda, therefore, you deduce is 1 minus 0.3 minus 0, and therefore is 0.7. Right. Now, this is true if that sum rule is true. Okay? Now, this sum rule has come from h square equals 8 pi g rho by 3 plus kappa by a square plus lambda by 3. And I divide throughout by h square, and then I have 3 h naught square by 8 pi g, that is rho over rho c, and therefore I have omega m and so on, right? So this omega m is rho over 3 h naught square by 8 pi g, and this omega k is k over 3 a naught square h naught square, and omega lambda is lambda over 3 h naught square. That's how I got that sum rule. So what I'm trying to say is that the sum rule simply re-expresses the Friedman equation. The Friedman equation is constructed and correctly describes a absolutely perfect, maximally symmetric space-time expand which has got just matter and radiation and curvature. If I extend that model, I would have, for example, what would be the effect of inhomogeneities in such a universe if the universe was not exactly homogeneous and isotropic? That problem has been solved by a man called Buchert, and he points out that in that case there is a correction to the Hubble equation. So you then have to describe everything in terms of average quantities. So you average over some domain of size A, and then you can write down a similar equation for the evolution of the domain size. And then you have an extra term here, and this extra term, right, would basically go as the variance of average of the variance of delta rho by rho square. Okay. So in other words, the more the fluctuations, the more this term would be. That term would then correspond to this plus a omega x here, right? So now my equation would be that omega x plus omega lambda is 0.7. And you would have to then tell me which one of them is, I mean, how do they split it up?
I see. But we can now also test homogeneity by looking at large-scale structure out to z equals 1.
Right.
And there's no evidence for such an omega x, right?
No, you can't do that because this equation that Buchert is talking about is on a constant time surface. The observations that you're making are along our past light cone. What you need to do, what we need to do, theorists need to do is to set up a framework that describes the effect of inhomogeneity along your past light cone. This has not been yet been possible to do, but there is a way forward. The way forward is to do a simulation of large-scale structure formation and then construct light cones in that and work out what your observable should be. Now, surprising though it may seem, it's only in the last year or 2 years that the first attempts are actually being made at genuinely relativistic simulations of structure formation. Everything has been Newtonian so far. These effects would not even have been captured there, right? And there are now 2 groups which do have simulations of structure formation, including relativistic effects, and they are seeing back reaction effects in their simulations. There is still a debate as to how large they are, because that depends on this variance. Now, if I say the variance is 10 to the minus 5 square, because that is the amplitude of fluctuations in the CMB, it's clearly negligible. But if I look at the present universe, the variance is of order 1. So the answer is anything between 1 and 10 to the minus 10. So that doesn't help us. I think the next progress will be made when these simulations actually converge and agree, and we have some understanding of what the effect of inhomogeneities is on the quantities that we measure, like the luminosity distance, the standard ruler, and other cosmological variables. That's one way to go. The second way with large-scale structure is that basically don't have much in the way of large-scale structure. We only have redshifts for about 1 million galaxies.
And the isotropic in the CMB part 10 to the 5 doesn't.
No, that would not have any impact on this question here. That says that the fluctuations were small at last scattering. If they only evolved under gravity until today, right? And then you have a inhomogeneous, that we understand, and the growth is perfectly consistent with what you would expect. However, that does not explain what I discussed in the first lecture, that you would then expect today's universe to have random velocities that fall off with the averaging distance, right? In the sense that you would have random velocities of order a few hundred kilometers per second, but if I average over bigger and bigger volumes, they should fall off, and I should then actually converge to the frame in which the CMB is truly isotropic rather than having a dipole. This is not being borne out by the data. The data so far show no convergence to the CMB frame out to 300 megaparsecs. So that is a serious issue. That means that there is no correspondence between the universe we currently live in and the ideal universe which should have made that prediction. If that problem can be sorted out, then one would be able to believe in the prediction from there that there is no such term as that, and one just has to live with these 3. But currently, we don't have any such term. We have only got these 3. And these were, of course, set out, as I pointed out, 100 years ago, and we are still using that model. I mean, on just general grounds, you could ask yourself if in 100 years there should not be some finessing of the model. But that finessing can be quite important, because ultimately it is the accuracy of that sum rule that will tell us whether or not the inference is correct.
Well, we have a lot of new sources from Maxwell's equations, but they're still just as good as they were in 1865.
Indeed. The Maxwell hit on a good one. Any other questions? No?
Okay, then let us set this figure.